Welcome to this explanation of the oxidative addition reaction that occurs in organometallic chemistry, and in particular here involving platinum 2 complexes. What is the actual point of the reaction that's shown in this article? So first of all, it shows the oxidative addition reactions as previously mentioned, but it also demonstrates the effect on the oxidation state and the coordination number of central compounds, and it investigates the isomerism of different ligands at varying temperatures with varying solvents, as well as looking at the stability of the varying ligands. So in full, you can see the reaction scheme for the entire reaction here, taken from the article, and you can see you have your starting cis and trans compounds, which are both square planar, and in reaction with I2, you form 3 and 4. Now 3 and 4 are our reaction intermediates, and they are octahedral complexes with the addition of this iodine. Now upon warming both of these complexes, you will form the final product of the article that the article shows, and this is compound number 2 over here. Now it's interesting that both intermediates form the trans product here, but the 1B conversion is quicker than the 1A conversion. Both intermediates actually go much faster when toluene is used over acetone. It's also really important to note that the intermediates are both clear products of oxidative addition, and this can be proven later on. I will explain in the analytical techniques how we can see that both of these intermediates actually exist. But first of all, it's important that we go over some electron counting and discuss the oxidation states of both our starting materials, our intermediates, and our final product. So if we start with our cis and trans square planar starting materials, first of all, we have a platinum 2 D8 configuration in both cases. Now this D8 configuration will give us 8 electrons overall for the whole compound just off that central platinum atom. We have 2 fluorobenzene ligands in each case and 2 triethyl phosphine ligands in each case, which will both donate 4 electrons. Now this will come to a total count of 16 electrons, but we also must consider that the phenyl eta 1 ligand of the fluorobenzene is anionic, and to balance this we will have a +2 oxidation state on the platinum, as our triethyl phosphine is neutral. It's a slightly different situation here for compounds 2, 3 and 4, but it's the same principle applied for the electron counting. So we have our platinum 4 compound in this case with a D6 configuration, as there are 2 ligands binded, 2 extra ligands binded, and these 2 extra ligands are 2 iodine molecules, which will give us 4 electrons. We also have the D6 configuration only giving us 6 this time opposed to 8, but we still have the 2 fluorobenzenes and 2 triethyl phosphines, which will give us 4 electrons each, which adds up overall to 18 electrons. And in this case, the 2 new iodine atoms are anionic ligands. All the others remain the same, so this will give us a 2- charge on top of what we already had, so our platinum atom will become +4 in its oxidation state. Small issue that is discussed in the article that is definitely worth noting is that the reaction of the cis and trans square planar complexes with xenon difluoride actually gives a very similar product, whereas the triethylphenyl groups are in axial positions opposed to the iodine. Now, this product cannot be formed in a single step, although it is actually the thermodynamic product, which means it is more favourable. But they could not isolate this product to look at the mechanism, as xenon difluoride is a very reactive and highly soluble substance. Now for the interesting part, how does this mechanism actually work? So we have our central atom with a lone pair, and the lone pair on the central atom actually attacks this delta positive iodine, and the electron density moves from the dihalogen bond onto the other iodine. Now we have our complex, which is positively charged overall, and it's quite simple really. The other iodine molecule is free to come and attack here on the platinum, and this forms this diiodo complex with the halogens in axial positions. The mechanism is fundamentally the same for both cis and trans isomers, but as you can see here, the fluorobenzene groups are trans, as are the triethyl phosphine, and it's the same here. Okay, so now moving on to the analytical techniques used in this article to study the reaction in detail. First of all, we have our ORTEP diagram here, which comes from the X-ray diffraction analysis of the final product, and you can see the general structure that has been previously discussed, as well as you are able to actually calculate the bond lengths from these X-ray diffraction analysis diagrams. So we also have, more importantly, our 2 NMRs here, which are both 31 phosphorus NMRs, and in the first NMR you can see in spectra B there is a large phosphine splitting of 145.5 Hz, which translates to the fact that the phosphine ligands in compound 3 are not trans, whereas in the second NMR spectra, in the middle NMR spectra B, you can see that this is indicative of the trans isomer, and this is because this shows a triplet for the CH2 group of triethyl phosphine, and there is no significant JPC coupling constant for the ipso carbons, which are the carbons where the fluorines connect to on the aromatic ring, and therefore showing the cis positions of these aromatic groups. I just wanted to note that all the images used in this presentation were from the first reference that I have below, and the second reference was also used for information as well as the first.